Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So in this talk, I will talk about real machine learning application. So we apply some distributed machine learning methods to a real application. This is actually a joint project with an internet company in Taiwan called Bridgewell. It's a Taiwan-based company specializing in internet advertisements. Yeah, the name of the company is called Bridgewell. That's a Taiwan-based company. Their business is mainly right now in East Asia for computational advertisements. Yeah. Baidu is in China. Right now, they don't have big business in Taiwan, I think. And also, Baidu is not only is mainly a search company. Okay, advertisement is part of their Baidu's business. Okay, so and the target application is for click-through rate prediction. So to talk about CTR prediction, first we need to say a little bit about the internet advertisements. The main purpose is that to find the match between users and also those ads. So for example, if you are if you type a query at Google, and they want to show you something, well, they need to match your interests and also their available ads. In general, an advertisement system is like this. So they have a so-called pay-per-click model. Of course, there are many different models, but this is one of them. So that means you will be charged if your ad is clicked. Yeah. So roughly, if you have so this is for search advertisements, it's like this. In the whole framework, you need to do you need to have a learning procedure to predict the click-through rate. Then once you have the click-through rate, using the CTR information and some other information such as the amount of money that people would like to pay, then you decide what to show for advertisements. Then probably you do some post-processing. Then you display the ads to users. Then from users' click behavior, then you get some past feedback. Then you collect their log. Then from the log, you do the training again. So there is such a cycle. That's a typical way for computational advertisements. So this click-through rate is an important component. Okay. It's not the only component. The whole advertisement system is very complicated, but CTR prediction is certainly an important one. The definition of CTR is like this. That's basically the number of clicks divided by the number of impressions. So impressions basically means a kind of page views. So like among so many page views that users have provided, then how many of them they click on the ads. So this is the CTR rate. Then for those internet advertisements company, then usually you calculate this CTR times this amount of bid to rank those advertisements. So roughly using such a value, then you can have a rank of all those advertisements. Then of course, you want to show the top ones so that that increase your revenue. There are many existing works on CTR predictions. Here I list two representative ones. In this KDD paper, they talk about the Google CTR prediction system. And in this paper, this is about the CTR prediction at Microsoft. Then I want to argue that CTR prediction can become a binary classification problem. The way it works is that all the click-through events can be considered a sequence of data instances. So at one time point, you have features collected for a user. That's the behavior of the user. So you have a bunch of features. And in the end, you know whether this user clicks on this ads or not. So this is like a negative label. But if for the next instance, you also have features, but you get a clicked instance, then that's like a positive label. Therefore, you have a binary classification problem.
So just to clarify, if he does not click, that's negative?
Yes, yeah. In a general CTR setting, we have only positive and negative. So positive means click, and the negative means not click.
That's quite noisy.
Yeah. Okay, so now we have a binary classification problem. There are some special properties about CTR prediction. First, this data set is highly unbalanced because most of the data instances are negative. Only very few of them, they are positive. Therefore, evaluation criteria cannot be accuracy anymore. Usually, people use AUC. This is basically area under the curve. That's the major evaluation criteria. There are a bunch of other criteria for unbalanced data can also be used. And about features, so for example, the type of these advertisements and the browser that the user is using, all those things can be considered as features. But I'm not going to focus on features in my talk today. So now we have a binary classification problem. We are going to train a logistic regression to get a model. So what is a logistic regression? The basic idea is that for any label feature pair of y and x, then you assume a probability model. So that P of this label given x is this 1 over 1 plus exponential something. Yeah, that's the logistic model. So this vector W is a parameter to be decided. So that's the probability model. Now let's assume that we have obtained a bunch of training instances. That's our training set. So here I denote YIXI, this I from 1 to L as my training set. So they are my training instances. Then logistic regression defines this weight vector W by maximizing the log likelihood. Now we are given so many training instances. You just calculate the product of all the probability values and you maximize this. So this becomes a maximization problem. But usually we minimize the negative log likelihood. Then plus a regularization term. In the end, we get the so-called regularized logistic regression. That takes such a form. You minimize over a vector variable W, and there's a regularization term, this W transpose W over 2. Then plus C times a summation of, this is actually logistic loss. That's a kind of training losses. So C is a parameter to balance between regularization and the training losses. So this becomes the standard form of regularized logistic regression. But now for CTR prediction, the data set can be pretty large. So we want to design a distributed Newton method to train regularized logistic regression. And we intend to use a Newton method. What's the basic idea of Newton methods? First, you calculate the second order approximation of your objective function. Then you minimize over it to get the search direction. And here we call it the Newton direction. So specifically, if WK is the current iterate of your model vector W, then the second order approximation is actually the gradient times our search direction S, plus this is health times S transpose times this Hessian matrix, which is the second order derivative. Then again times this vector S. So we hope to find this S, which is the Newton direction. So we know how to update WK to the next iterate. That's the basic idea of Newton methods. And this minimization of the subproblem can actually be written in the same way of solving a linear system. Okay, please notice that this is an unconstrained quadratic function. So minimizing it, you just make the derivative over S to be 0. Then all you need to do is to solve this linear system. But what's the problem of solving this linear system in order to get the Newton direction? Well, the main problem is that this H matrix is going to be too large, actually too large to be stored. So how large is this H matrix? The size of this H matrix is n by n, where n is the number of features. The reason of that is because our number of variables, that's actually the size of the vector W, is exactly the same as the number of features. So this is going to be large if your number of features is quite large. Yeah. Oh, okay. It depends. It depends. In the experiment I'm going to show, for CTR, actually right now my number of features is not so large. It's not so large. But number of data is pretty large. So not only the storage, but also the calculation of this H matrix, that's another issue. But in my experiments, I do have some other data, okay, other than CTR. Their number of features is pretty large. Yeah. So now we have basically recognized that the storage of the H matrix or the calculation of H matrix may be difficult. But fortunately, for logistic regression, this H matrix actually has a special form. It is equal to this I is the identity matrix plus C. Remember that's the regularization parameter. Then we have this matrix X transpose times the matrix D times matrix X. So what is X? X is actually the data matrix. So each row of this X is actually a data instance. We basically put all the instances together into one matrix. That's X. And D is a diagonal matrix. And for logistic regression, the diagonal elements takes this form. So the DII will be this exponential something over 1 plus this exponential value. So this H matrix has a special form. Then what we can do is to use conjugate gradient method to solve this linear system. So remember that to get the Newton direction, all we need right now is to solve this linear system. Then we decide to use a conjugate gradient method. That's one type of iterative method. Okay, for any linear system, you can use either direct or iterative methods. Direct method means like Gaussian elimination. But for iterative methods, conjugate gradient is a very commonly used one. And for this conjugate gradient method, all you need is a sequence of so-called matrix vector product. And right now, our matrix happens to be this Hessian matrix. So all we need is a sequence of Hessian vector products. If you look at this Hessian times a vector S, then because of the spatial form of the Hessian, then our Hessian times S can be written as this sequence of matrix vector product. So remember this X transpose dx is the most important part of the Hessian matrix. But now instead of trying to calculate that matrix first and multiply it with S, I calculate X times S first to get a vector. Then D times this vector, because D is diagonal, so this multiplication is very easy. Then I do X transpose times this vector. So now we have a so-called Hessian-free approach for the Newton method. Okay. Because traditionally, for applying Newton methods, you got to have the Hessian matrix. But now, by this technique, we are still using the Hessian, but without explicitly forming the Hessian matrix. So this is called Hessian-free. So this has been developed for machine learning in some past works. So for example, in this Journal of Machine Learning research paper in 2005, they use such a technique for L2 loss support vector machines. I mean linear case, not the kernel case. And this is our Journal of Machine Learning research paper. In that, we apply this kind of technique for logistic regression. And the people have also try to parallelize such a technique. So this is actually a term project in University of Connecticut. So this student actually apparently used actually parallelize the procedure in this paper. And right now we are. I'm also going to have a parallel implementation, and this implementation is actually extended from the implementation in the software liblinear. Yeah.
So how does it extend to the loss functions?
Oh, you mean other loss functions? Yeah. Oh, yeah. Okay. So roughly speaking, if your Hessian matrix has this kind of spatial form, then you can do Hessian-free Newton method. That's yeah, right. Roughly speaking. So for example, if you have L2 loss support vector machines, then you can do that. Okay. But on the other hand, you can think from the so if you consider quasi-Newton method like LBFGS, so LBFGS is actually intends to approximate the Hessian matrix by a finite set of vectors. So that can be considered as kind of a way to do Hessian-free Newton, but an approximate Hessian-free. Yeah. So I believe there are many possibilities. But here we are still thinking about exactly using that Hessian matrix. But happens to be that it has such a spatial form, so we can do that. Yeah. Here I'm not doing LBFGS. Our parallelization is mainly on how to parallelize this Hessian.
Yeah, but will they apply for LBFGS? Will they apply for what are the challenges? What are the challenges in applying your parallel algorithms to LBFGS?
You mean the challenge? Okay. So here, of course, there are several ways to implement this matrix vector product. So that's a challenge, you can say that, because then different implementations may give you different scalability. And for LBFGS, essentially you also need to do a matrix vector product. So the parallelization techniques are similar, I think.
Can I ask an observable question? So this LBGS versus Tron, right? I mean, are there cases where you have seen that what is your take on this? I'm more asking for a personal opinion. That if you consider LBGS equals trust region Newton method, I mean, is this the case? Trust region always is better than LBFGS, or do you consider the specific structure of the problem where you see that LBFGS is better than Tron and Tron is better than LBFGS? Because this is one confusion people already always have, that which one should we use out of these?
Okay. Yeah. So basically, his question is to ask my opinion about Newton method and LBFGS. LBFGS is a quasi-Newton method. But if you look at the history of optimization, after like 3 or 4 decades, quasi-Newton and Newton are still there. So the short answer to yours is they have their strong points in different situations.
So is there structure to that?
Yeah.
Is there structure in the sense looking at a problem? Is there specific structure in the problem where I can say that you should apply this method or you should apply that?
Oh, okay. So from the optimization viewpoint, usually for optimization researchers, they don't particularly say problem structure. Okay. So the difference between quasi-Newton and Newton is that Newton, basically you get the so-called quadratic convergence in the end. So for a lot of scientific applications, sometimes you need very accurate answers in the end. Then in those situations, quadratic approximation is good. But sometimes you don't need that, right? But in that case, probably you want to go with quasi-Newton or even first-order methods. Because roughly, that's the differences. Yeah.
Does this approach work for other regularization like N1? Does this approach work for other kinds of regularization like N1?
Oh, wow, that's a good question. The short answer is no. Right now, this doesn't work for L1. Yeah.
The biggest cost anyway in LBFGS is the matrix vector product, right? And that's the same cost. So there is a left multiply and then there is a right multiply all the time. So it's the same here.
Yeah,
but
that's right.
every step of your CG, you have to do exactly the same amount of work, essentially.
Yes, that's right. That's right.
So now the question is that,
Yeah. Yeah. Yeah.
there's like an iteration of Newton, and then there are iterations,
Yeah,
some
yeah, that's right.
iterations of.
That's right.
So,
Yeah.
and typically in 30 to 50 iterations of LBMS, you
Yeah.
have a reasonably good solution.
Yeah, yeah.
When do you start getting a good solution?
Oh, yeah. Okay. Yeah, that's a good question. So essentially, what you are saying is that the comparison between Newton and the quasi-Newton on one computer and on distributed systems may be different. That's right. So we need more, a bunch of serious comparisons. Okay. So to answer you, we are trying to do a serious comparison between Newton and quasi-Newton in a distributed system. But that's not the focus of this talk at this moment, because for the job of this talk, I need to finish that product with that company. We need to have something deployed. Yeah. So,
No,
yeah.
I'm not talking about serial versus.
Yeah.
I mean, that is an optional issue to me,
Yeah.
right? I'm saying that one iteration
Yeah.
of
Yeah.
LBMS.
Okay. So usually the number of CG iterations in general, you don't need many CG iterations.
Because you can hot start also from it.
Yeah. Right. Yeah.
But how many outer iterations?
Oh, outer is very small. Usually like 5 or 10, these kind of things for Newton method.
Iterations, roughly how many?
It depends, but I would say in general, okay, if that's a good situation, that's like 30, 40, these kind of things. That's possible. Yeah, and also depends on when you start when you stop the whole procedure. Yeah, so it depends. Yeah.
Sorry,
Yeah.
you're saying you have you said you have 5 feature iterations, and how many CG iterations?
Oh, okay. So
That's for your specific problem.
yeah, right. Okay, the number of total conjugate gradient iterations also depends on like at each Newton iteration. So remember that at each Newton iteration, we need to solve this linear system. So you have a sequence of CG iterations. In fact, you can just stop at any time. You can say, okay, I just do 10 CG iterations, right? So you have 5 outer iterations, then the total becomes 50. That's possible. And actually, okay. Then there are many different kind of stopping criteria. But all you want is to ensure the overall convergence of the whole Newton procedure. So what I'm using here is the so-called relative stopping condition of solving a linear system. So you just check the residual of the left-hand side minus the right-hand side, then divided by the norm of the right-hand side. So that's a relative error. That's a very standard way to start an iterative procedure of solving a linear system. Yeah. Okay. So now let's try to check how we do this parallel matrix vector product. So the whole data matrix is now distributedly stored. So we have X1, this segment of data in node 1, and then assume we have P machines. So it's like this. And we notice that if you want to multiply this XD transpose XD, X times S, it's actually the same as the summation of if you use the first segment to do X1 transpose D1 times X1 times S, and plus the end. So now we want to parallelize this summation. So each machine will be responsible for one part. So we use an O-reduced procedure. Basically, the first node is responsible for this calculation. And again, we use a Hessian-free approach. Okay, so we do this matrix vector first. So in the end, we get a vector. And after that, we use an O-reduced procedure so that all the nodes, they get this matrix vector product. And at this moment, we are using MPI for the implementations, but even though we can use other programming frameworks. So, yeah.
Do you have any sense for the structure of these matrices? Are they dense? Are they, is there some sparsity to them?
Okay,
are
yeah.
you exploiting the sparsity?
Yeah, that's a good question. So for CTR prediction, basically the data X is sparse. It's very sparse. And so it's true that now synchronization is going to be an issue. We are developing some other techniques, try to make the computation to be more balanced. So that can be done. But at least right now, for this, we just say we randomly partition data to several segments and do this procedure.
There are some very nice techniques that handle different types of sparse structures for many types of computations. So you don't have to reinvent the wheel.
Yes, there are different ways to store sparse matrix and also for the computation. But I'm not sure because right now this is a little bit special. Because remember we are doing that hashing free, these kind of things. So not sure. I need to check. I would say that. Okay.
Maybe we can talk about
Yeah.
So you store X in X transpose or because you have to do an X transpose?
Oh yeah. Okay. Right now we are using the row-oriented, so that's instance-wise storage, because when you do matrix vector product, you don't have to get transpose. So even if you do the row-wise storage for calculating X transpose times a vector, that's very easy. Yeah. But then, of course, we can also do this feature-wise storage. That's another story. Yeah. So essentially what we do is that we let every node to have this, sorry, I need to put S because this becomes a matrix. So we let every node to have this hashing times vector S. Then it's like after getting that hashing vector product, then each individual node, they run a Newton procedure to update their W vector. So immediately every node has this weight vector W. So they maintain. Okay, so we don't need to do the communication on this weight vector. Then I want to talk about our system architecture. Yeah. Yeah. Okay. So yeah. So probably you want to ask, what if the number of features is larger than the capacity of a computer? Yeah. Then the answer is right now our design cannot handle that. Yeah. So you have truly large scale number of features, then no, we need to do something else. Yeah. So right now we basically assume that our weight vector can be stored on every single computer. Yes.
Do you face any numerical stability issues in your computation?
Can
Numerical stability issues. Do you face any numerical stability issues? Inaccurate computations happening over front of the
No. So sorry, I don't get your question.
Numerical stability issue.
For
Encounter any numerical stability issue?
but okay. So but I don't quite understand what you mean numerical stability. This kind of Newton approach, that's a well-developed technique. So so usually when people talk about stability of Newton methods, that means the convergence speed, or say the number of iterations. So of course, if the problem is more well-conditioned, then the number of Newton iterations that you need is smaller. Otherwise, you need more iterations. And in our situation here, that is related to the parameter C, or say the regularization. Because when C is small, then the regularization term dominates. Then you have a very well-conditioned problem. So you can finish in one iteration for the Newton method.
I think that you're adding this regularizer there, always there, right? Which makes sure that a computation is fine.
Oh yeah, right. That's right. Yeah. For the whole system, actually we are running this on Amazon's system. So the data is actually stored in Amazon S3. So that means for the company product, all the new data will go there, will be stored there. But for the training, for the training, we need to move data to different local disks. I will talk more about this later, because this also takes time, right? Then after each local disk gets data, then we need to do the so-called encoding and the training procedure. So encoding means feature generation. I need to generate features in a parallel way. Because we only move some kind of raw data into each local disk. But from the different features, probably we need to do some kind of interaction to generate new features. Yeah. So there is an encoding procedure. Then after that, we do the parallel training. So after training, then we get a model. Then that's for practical use. Then again, we get log. Then we go back to the storage. So roughly, that's the system. So let's do some experiments. Well, this table actually shows you the cost of renting things on Amazon. Well, for us, it's just not cheap. Yeah, but anyway, we use that for experiments. And for computation, computation is done at Amazon EC2. So what we use is basically we rent each node to be such a machine. And the way on Amazon to say how powerful a machine is, they have a standard unit called ECU. So ECU is like 1 gigahertz of a particular CPU. So now I say, okay, I want to rent a CPU with such power, this kind of setting. And also about the cost of renting a machine. Actually, they have two types. One is that you share that machine with others. Another is to say, okay, I rent this machine and I want a dedicated one for my use. Then, of course, for the second type is much more expensive. And also, we need some additional tools for the whole configuration of the system. And I show experiments on 3 data sets. So the first one is the real CT. I think this is the average one. Okay, so so their unit is like 1 gigahertz of a 2007 CPU, and mine is like so-called 6.5 such unit. So it's the typical machine, I would say. Well, that depends on for the experiment setting. So if I want 64, I go to rent 64. If I want 16, and I rent 16. So I'm going to show results of using different number of nodes.
The reason I was asking is, you mentioned all reduced, and when I talked to John Manford, everything is hunky-dory, that's fine. And when I talked to Alex Moller, he really hates this because he says all of John's experiments were done on these high-quality trusted machines which never fail. You want to try this on Amazon's services. If machines start failing, then you want to get big problems with all reduced.
Yeah.
It's not fault tolerant. I mean, that's kind of orthogonal thing. You want to bring in fault tolerance.
Yeah.
As you start scaling out, right? I don't know for CTR how many nodes you're going to use.
Yeah, there are all kinds of such issues. But basically, now we just want to construct a system so that we can use. Yeah. So, yeah. And to answer your question is that this is not a very high-end machine. I mean, a reasonable one. Yeah.
They have these names, like it's an X1 large or.
I don't think we use. Well, I'm not familiar with things you talk about. I think we just use some typical ones. Yeah. So now about the number of data and features for this CTR data set. So we have like about 300 million instances. But for right now, for our basic setting, the number of features is not large. It's only about 6,000. But we also take 2 other data sets, publicly available data sets for experiments. So this web span has about 350,000 instances, but has a lot more features. It's about almost 20 million features. And this epsilon is a dense data. So it has about 400,000 instances, but 200 features. Yeah. So just try to have a set of different data with different properties to see what happens. Yeah.
So the webspan dataset, is this from the Yahoo dataset or somewhere else?
Oh, no. This is not from Yahoo. This webspan was from the ICM, or Large Scale Machine Learning Challenge. They generated, what they did is, kind of artificially. They download a bunch of web data, and they have span or non-span. And they generate the trigram of that data set. So that's why you get so many so many features. Yeah. But you can download it, say, from my web page. Let's check the running time analysis. So this is for this epsilon. So remember, it's dense data. And I try to list different time for different components. First, there is the loading time, and then the computation time, and then the communication time. And this table actually looks very nice, because what we can see is that the important thing is about the loading time. Actually, the reduction on loading time is almost perfect. But this is reasonable, right? Because there's no interaction between those loading tasks. And computation is also reasonably good. But communication, then, of course, when you have more nodes, then it is. But for this case, it's very good. So the overall scalability is actually very good.
Do you remember number of iterations?
Iterations? No, but I can give you the numbers later. Yeah.
Because what's interesting is that the loading computation time are approximately similar. It basically means that number of iterations will exactly give you the speed up of communication versus the success, right? So interesting to look at that.
Yeah. Okay. I can try to check such.
You are loading from a text file?
No, we do binary. Yeah. So there are many. All kinds of weird issues in this kind of comparison. Yeah.
So, what are the absolute time frames? Sorry, I can't see. What is your total time optimization time?
Total optimization. Okay. So in terms of running time, that means for this parallel setting, that means computation plus communication, right? Because then usually you don't count the loading time as part of the optimization procedure, right? But I still list the loading time here, because for real application, then you need to consider total time.
Right, but the columns don't have, are you missing another component here? I mean, like, if you look at 16 nodes, you're saying the loading time is 19.1, and the computation is 14.1, communication is 1.4.
Yeah.
That sums up to 34.6. You're showing is 40.6.
Oh yeah. Okay. I think that's a good thing. Well, I need to check. Probably synchronization is something that we didn't show here. Yeah.
The reason I asked the question in the first place is because you're getting unbelievably good speed up as far as loading time and compilation. I mean, it's perfect. You multiply 19.1 by 16. That gives you very close
This one is really good. This one is really.
That's actually super linear.
Yeah.
Whereas if you multiply 14.1 by 16, that's pretty close to 224. So something going on here that
Yeah.
clear.
Okay, so I can go to check the details. But I think probably we miss out some information in this table. I believe it may be synchronization or something.
That should be part of communication also.
Yeah, we can do that.
And what are the units only? It's like seconds or minutes?
Oh, this is seconds. But this is a good case. This is actually a good case.
And this is on the CTR dataset?
This is not CTR.
What
Yeah.
is your, are you also telling me what your precision equal area under the curve is?
Can you say that again?
Are you also listing your area under the precision equal curve somewhere?
You mean coefficients, or you mean the W vector? No. The
Performance.
performance. Okay. No, this one actually we don't care about the performance, right? For this one. Okay. But for CTR, I'm going to. Yeah, for CTR, I will show. For CTR, we will show that. So this is the. And this is the result on CTR. So this is a small subset, only 60 million. The reason for using a subset is because we are able to use one node of Amazon machine for the whole job. This is still good. This is still okay. Still okay. You want okay? So the total time. This is for using one node is about 790 seconds, and for 16 nodes, this is about 79 seconds. Yeah. Huh? 16. 16. Yeah. Yeah. And here's the result of using a larger one. And for a larger one, we can start only from the 4 nodes. So for the 4 nodes, we have about 1200 seconds for the training. And when we increase the number of nodes up to 64, then this is about 125 seconds. Yeah. Yeah. Oh. No. Let me see. No, I think there's. No, yeah. There's there. Okay. So. Okay. Yeah. Right. I think so. Yeah, I think so. I think this is a problem that when we try to generate a table by having only one digit after the decimal point, then apparently we made some mistake. Yeah. So you are right that this should be 1,000. Yeah, this one should be 1,000. Yeah.
But what you're missing cannot be synchronization time, right? Because even in the single node case, if you go back to the previous slide, even in the single node case, the numbers don't add up, and there is no synchronization in the single node case.
So they are.
So I guess when you say computation time, right? Is it average time per node, or what kind of time is computation?
But this is only one node. Yeah. So I think probably, but well. The summation of those two values is almost the same, but slightly different. So we need to check like how we obtain the time. This is one node. This is one node. Yeah, but the summation is already very close to this one, but there's a small difference. So that's something we need to check. I think that may be related to how we calculate the time of different components. Yeah.
Because that whatever you're missing seems to keep growing as the number of nodes grows.
Yeah. So probably we mainly look at the total time at these moments. That's more accurate. So then let's check the scalability. So by scalability, I mean that while we double the number of nodes, we also double the data size. And then, of course, we hope that under perfect scalability, the total time will remain the same.
Did you run your experiments on dedicated machines or will you share?
No, actually, this is shared with other people.
So
yeah.
Is this total time work clock time or is this?
Yeah, this is a kind of work clock time. Yeah. So all those are issues. I mean, in getting such information.
You also want to show a plot of area under the curve versus pi.
I will show something on that. Yeah. So we try to check that if you double the number of nodes and also the size, then how is the result? I guess let's look at those two. Okay. Okay. We are running out of time, so let me just show two figures. So let's look at this web span. This web span has a large number of features. No, is this the number of features that I showed earlier? Seems to be smaller. Yeah, okay, so this is actually the, okay, there's a reason. So, I mean, for the design of the whole parallel experiments, there are many, many issues. For this one, I'm not using the whole set. I use a subset. Then I keep doubling the copy data to different nodes. Okay, because I want to do certain control. Yeah, so that's the reason why my number of features is actually smaller. Because I start from a smaller subset. But anyway, let's just look at the result. So the main problem is that we see that communication cost is actually a concern. That's the main conclusion. And the reason is simple. So we see that scalability is going to be better if your number of features is smaller, because then your communication cost is lower, right? But when your number of features is larger, because you have to transfer so many elements to different nodes, then of course, then your scalability is not so good. Then in this slide, we try to check the performance. And what we are interested in here is to ask a question. In a real world application, so we say, okay, if we keep increasing the number of training data, can we really improve the performance? So we draw such a figure. This is AUC versus the data size. But actually, for the AUC, we can only show the relative improvement because this is related to the business information of that company. So roughly, you can see that when we increase the data size from a smaller one to about 200 million, then we basically reach the best AUC. After that, even if you increase the amount of data, at least for the current feature setting, then you don't get much. So, here we haven't done any experiments on nonlinear classification at this moment. So I just said that if you have 200 million instances, then that's already give you basically the best AUC. But what's the size of data with of such data set? Actually, the size is only around 18 gigabytes. So naturally, you ask a question: do we really need a distributed setting? So why not just copy the whole data to one machine, and we can do the training, right? Yeah. So this is actually an issue worth for that we should try to address. So now I will have some interesting discussion. So the first question that I ask myself is that, do I really need a distributed system? So I try to check this one machine versus distributed environment. I mean, let's just look at the CTR result. If you look at the total time, so this blue solid line is the total training time of using different number of nodes. And this blue but dotted line is the training time of using a different number of cores on one machine. But I also list the loading time. So if you look at this red solid line, that's the loading time of using a distributed system. And if you look at this red and the dotted line, that's the loading time of using one machine. Of course, it is a constant, right? You have only one disk and a fixed amount of RAM. Yeah. So the loading time remains constant. This is actually an issue. And because of this reason, you can argue that probably doing distributed setting is useful, because then you get parallel data loading. Yeah. So not even talking about the performance of doing parallel optimization. The parallel loading is something very useful. And for the optimization algorithm, what we have found out is that after we increase the number of cores, then up to a certain point, then the running time does not decrease that much. So the problem is that even though you have right now for our setting, we have 8 cores. But just in a one machine setting, you need to move data to the upper level of the memory, so CPU, so those cores can use them, right? But for our calculation, CPUs are very fast, but moving data up to say level 3 cache is relatively slow. That's the reason why we don't get good speed up. Yeah.
So when you had talked about, so there is also this, so let's say the system I told you, I don't know what the meta system, so I can't comment on it, but there is a job setup cost also, which is like, let's say in the mappers, I want to, first the data needs to come from, like, there's a concept of locality there, but it's not always the case that,
Oh, you mean for the distributed, like moving data to the local?
Yes.
Okay, I will talk about that. Yeah. And for our setting, that part is not an issue. So I will explain why. Yeah. So this is a simple comparison between the advantages and the disadvantages of two settings. But let's skip this. So this answers your question. So in my figures in the above slides, actually I didn't include the time for moving data to local disk. Okay, before I start running this MPI job for parallel Newton method. So how do we handle that? This is not an issue for us. So for our application, actually we use data in a sliding window. So that means, suppose we want to train data in the past week. Then after today, then for tomorrow, then we just keep moving and we throw away past data. So we are not going to train data in, say, 3 weeks ago, at least for the current setting. So what we have done is, right now we just spend some money to keep renting some local disks. And for any new coming instance, they are immediately dispatched to a local disk. So it's like they are already stored there. And then, so this data moving is completed before training. So when we decide to do training, we go to, at Amazon, we can rent machines to mount those local disks. Okay, so now we don't have the data moving problem. That's how we solved this. Yeah. And, but by this setting, of course, data are also constantly removed from the local disks. Then I want to talk about the issues of the workflow, because this is the whole real application. I'm going to finish soon. So I want to say that distributed training is only one component of the whole workflow. If we check the system architecture, so I need to, as we have mentioned, we need to handle this data movement, but also feature generation. So training is only one part. And I have mentioned that since we are able to handle this data management issue, but we found out that for our real application, data encoding, that means feature generation, can be very time consuming. So here's a reason. Suppose we have a feature called a fruit, and each node contains some kinds of fruits like this. Then in practice, we may not know what kind of fruits in advance. But then now we want to encode them to different numbers. So eventually we want to generate such indices on different nodes. So this again is a kind of parallel process. This is actually quite complicated for our case. So in the end, at least right now for our system, what I can tell you is that this encoding takes more time, may take more time than the training. But I need to say not for that setting of 5,000 features. Because of this, for this experiment, I'm not doing, I try to use some only simple features. Okay, but what I want to tell you here is that if you are working on a real system, then training is only one part of it. There are many other weird issues. Yeah. So this is the last slide. So for the optimization part, of course, being an optimization researcher, we are interested in comparing other optimization algorithms, such as cosine Newton or ADMM and a lot of others. But the lesson of this work is to show that first, looks at least for this application, distributing the Newton methods are enough for our use. And then for a practical big data application, there are many, many issues beyond this machine learning. Yeah, that's my conclusion. So thank you very much.
So I have a question. And this is part of a comment, part discussion, part question. So I've been thinking about CTR a lot as well. She's done work on this. And when you're looking at real world systems, I would like to really emphasize that the training is really one tiny part of the system. And we are trying to justify this in terms of area under the precision recall curve, training time, etc. And I'm not sure any of these parameters are actually really important in the real world. So for instance, particularly with CTR, I think one of the most important things that you need to do is speed of experimentation.
Yeah,
Not necessarily your area under the curve. So what will happen is, whatever system you design, your advertisers and users will react to that.
Yeah.
Your CTR will come back
yeah.
down with time. And what you want to do is, you want to be resistant to spam attacks, you want to be resistant to variations with time, etc.
Yeah.
And so you really want to enable your engineers to carry out experiment after experiment. What happens if I add one more feature to the product?
Yeah, that's very right. Yeah.
And so over here, I'm not really sure whether I would even want to do distributed. So what happens if I just do, let's say, stochastic gradient descent? How close would I get?
Okay. So essentially, what I have said is that even for CTR prediction, it's already complicated enough. But you can even argue that maybe CTR prediction is not a useful component for the whole advertisement, right? So who knows that? So then, in an internet company, then if that's a good one, then usually they need to have very many smart designs. So for example, you can easily do A/B test. Those things are very, very complicated. But you argue that, say, probably just use some simple methods. Okay, but for me, this distributed Newton is simple enough. So I just take it, just plug it into the system for my use. So that's my answer to your question. So
I'm not clear. What I'm trying to say is, if speed of experimentation is paramount, you want people to be able to run experiments on their own individual boxes without needing 64 cores or 64 nodes or something like that.
Yeah. So essentially, you're saying probably those experiments are not meaningful. Well, that's partially right, but this is a distributed machine learning workshop, so we try to show some such results, right? Yeah.
I have a slightly related question, which is, if distributed Newton you think is simpler, and then why don't you just use the tau toolkit for optimization, plug it in, and you essentially get logistic.
Right. Okay. Yeah. What we should say is that there are a bunch of existing parallel. So optimization people, they have done some existing parallel frameworks. Yeah. But maybe my answer to that is, because to implement that parallel Newton is probably easier for me to figure out how to use those existing optimization packages. So,
it's literally like 10 lines of code to implement logistic.
but to embed, so you mentioned this tau. Tau is an MPI based numerical. That's an MPI based numerical optimization and PDE packages. So the most time consuming part for us is for all the other part to construct the whole system. Yeah. So so for us, say, writing the Newton method is extremely easy, but then we need to spend some time to connect this Newton implementation and the whole system, right? So even if we use other things, we still need that. That part can be time consuming. Yeah.
But I mean, the advantage of using some other toolkit would just be that you would have other optimization methods. If you
Once we have that, that's right. Yeah.
Also, you didn't mention anything about the data imbalance and the fact that if you just assume negatives to be things that are not clicked to be negative, you have a lot of noise in your training system.
Well, that's a whole other issue, how to handle imbalanced data. So, but here we yeah, we don't try to address that. We just think we just try, okay, first we have an absolute value of AUC, right? But the more important thing for the company is probably to check if this new system is better than the previous one. But if the answer is yes, then that's good enough. That's actually the situation.